Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. A secure software development lifecycle, or secure SDLC, is a structured way of creating software where security is woven into every stage, rather than added at the end. In traditional environments, teams often discover vulnerabilities late, scrambling to fix them just before release. That reactive model is costly and risky, especially for artificial intelligence systems where datasets, models, and pipelines bring unique exposures. A secure SDLC for AI adapts the traditional concept by embedding security into data preparation, model training, validation, deployment, and ongoing operations. This integration ensures that controls are not isolated tasks, but continuous practices. The key benefit is prevention. Vulnerabilities and compliance issues are addressed early, reducing both costs and risks. In AI, where workflows involve sensitive data and rapidly evolving models, embedding security throughout the lifecycle is the only way to achieve reliability, trust, and resilience at scale. Planning phase security creates the blueprint for the entire secure SDLC. Risk assessment at design evaluates what could go wrong before resources are committed. This includes understanding potential data exposures, model misuse, and adversarial vectors. Defining trust boundaries clarifies which components, such as datasets, APIs, and orchestration tools, must be isolated and monitored. Acceptable use policies are set early, making it clear what the system can and cannot be used for, protecting against harmful or non-compliant behaviors. Compliance mapping aligns the planned system with relevant regulations, ensuring that requirements for privacy, fairness, and accountability are identified before work begins. This phase prevents costly rework later and provides a strong governance foundation, ensuring that security and compliance guide innovation rather than hinder it. Data preparation security focuses on the integrity and protection of the material that will shape AI models. Dataset vetting ensures that sources are trustworthy and free from manipulations or hidden biases. Labeling integrity checks validate annotations, confirming that humans or automated systems have applied them consistently and accurately. Secure storage procedures keep both raw and labeled data safe from tampering or theft, using encryption and controlled access. Provenance documentation records where the data originated, how it was processed, and who interacted with it, enabling accountability and traceability. These measures recognize that compromised or poorly managed data undermines every subsequent stage of the lifecycle. By applying strong controls during preparation, organizations safeguard against poisoning, privacy violations, and reputational damage long before training begins. Model development security ensures that the code and pipelines supporting AI workflows are robust against attack and error. Safe coding practices apply to scripts and infrastructure just as much as to application logic, helping prevent vulnerabilities from being introduced during implementation. Dependency scanning checks third-party libraries, which are common in AI, for known vulnerabilities or malicious code. Secure experimentation environments isolate research activities, preventing inadvertent exposure of sensitive data or model artifacts. Version-controlled discipline ensures that every change is documented, reviewed, and auditable, reducing the risk of shadow code or untraceable modifications. These practices transform development from a loosely managed process into a controlled environment where both innovation and security thrive together. In AI, with rapid iteration cycles, disciplined model development security is essential to maintain trust. Training phase security protects the computationally intensive process of building and refining models. Controlled compute clusters enforce access restrictions, ensuring that only authorized users can launch or modify training jobs. Monitoring training runs allows teams to detect anomalies, such as unusual access patterns or performance issues that may signal adversarial interference. Securing checkpoints prevents the theft or tampering of intermediate model states, which are both valuable intellectual property and potential attack vectors. Anomaly detection systems catch irregularities in model behavior during training, spotting poisoning or drift before it becomes entrenched. Because training often involves sensitive datasets and substantial resources, this phase is a prime target for attackers. Strong security here prevents compromises that could ripple across the model's lifecycle. Validation phase security ensures that models are tested not only for accuracy but also for resilience and compliance. Adversarial robustness testing probes the model with crafted inputs designed to trick or manipulate it, confirming that defenses hold. Privacy leakage checks verify that outputs do not inadvertently expose training data or sensitive details. Compliance verification ensures that the model aligns with regulatory obligations, such as fairness requirements or sector-specific standards. Bias and fairness analysis identifies unintended discriminatory behavior, reducing the chance of harmful or reputationally damaging outputs. By incorporating these checks, validation expands beyond performance metrics to include safety and accountability. For AI systems, validation is the final gate where technical, ethical, and legal requirements converge before deployment. Deployment security marks the moment when a model transitions from a controlled environment to exposure in real-world use, making it a critical stage for applying safeguards. Hardened inference endpoints ensure that attackers cannot exploit weaknesses in model APIs or overwhelm them with malicious queries. Authentication enforcement requires that only approved clients and systems interact with the model, reducing unauthorized access. Encryption of communications secures the flow of prompts and responses, preventing interception or tampering as data moves between users, models, and downstream systems. Logging of access provides accountability, creating detailed records of every interaction to support both operational monitoring and forensic investigations. Without these measures, deployed models become easy targets for exploitation. But with them, organizations can ensure reliable service, user trust, and compliance with regulatory expectations. Operation security sustains vigilance after deployment, treating security as an ongoing responsibility rather than a one-time event. Runtime monitoring watches system behavior for anomalies, including unusual traffic, adversarial inputs, or unexpected model outputs. Drift detection ensures that models remain aligned with their intended purpose, catching performance degradation or subtle adversarial influence. Incident response planning prepares teams for when issues inevitably occur, ensuring that responses are fast, structured, and effective. Policy enforcement applies acceptable use rules dynamically, blocking behaviors that violate organizational or regulatory standards. These practices ensure that AI systems remain resilient in production, adapting to evolving threats and real-world conditions. Operations security demonstrates that successful deployment is not the end of security but the beginning of continuous oversight. Governance integration connects the secure SDLC to enterprise oversight, embedding security into organizational accountability structures. Board oversight ensures that leadership remains informed and responsible for risk decisions associated with AI systems. Acceptable use policies, drafted during planning, are reinforced here, guiding operations and user behavior with clear boundaries. Regulatory alignment ensures compliance with data protection laws, industry mandates, and ethical standards, avoiding penalties and reputational harm. Audit trails document every significant security action, from data handling to incident response, providing evidence for internal reviews and external regulators. Governance integration ensures that security is not left solely to technical teams, but is supported and enforced at every organizational level. This integration transforms secure SDLC from a technical practice into a strategic business commitment. Developer training sustains security practices across the lifecycle by equipping teams with the knowledge needed to apply them. Training in secure coding for AI pipelines teaches developers how to avoid introducing vulnerabilities when building data ingestion, preprocessing, or orchestration systems. Awareness of threats ensures that teams can recognize novel risks such as prompt injection, adversarial attacks, or model theft. Knowledge of prompt security prepares developers to filter and manage inputs effectively, preventing misuse or manipulation. Lifecycle discipline emphasizes that security is continuous, not a task left to specialists at the end of the process. Training ensures that all contributors, from data scientists to engineers, understand their role in maintaining AI security. In effect, education embeds governance into daily practice, making security a cultural expectation rather than an afterthought. Continuous integration embeds security into the pace of modern AI development. Automated vulnerability scanning checks dependencies and pipelines with each commit, preventing unsafe code from reaching production. Regression testing pipelines confirm that security patches do not break functionality and that previously fixed vulnerabilities do not resurface. Configuration compliance validates infrastructure as code templates against governance standards, ensuring that environments are consistent and secure. Rollout mechanisms with rollback capability allow rapid recovery if deployments introduce unexpected risks or failures. By weaving these safeguards into automated workflows, continuous integration ensures that security keeps pace with rapid iteration. For AI, where systems evolve quickly, automation is indispensable. It turns secure SDLC from a theory into a practice that scales with innovation. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Metrics for a secure SDLC provide a way to measure whether the lifecycle is delivering on its promise of proactive protection. Tracking the number of vulnerabilities detected early highlights whether risk identification is happening before deployment, where fixes are costlier and harder to implement. Measuring closure timelines shows how long it takes to resolve discovered issues, providing insight into operational efficiency and responsiveness. Compliance scores, often based on audits or automated checks, indicate how well the system aligns with organizational policies and external regulations. Incident reductions demonstrate the ultimate impact of a secure SDLC, showing that security is not just theoretical, but actively reducing harm. By monitoring these metrics, organizations transform security from abstract goals into accountable, measurable outcomes, strengthening both technical defenses and governance credibility. Tools for secure SDLC make these practices sustainable and scalable. Dependency scanning tools automatically flag vulnerabilities in open-source libraries, which are heavily used in AI pipelines. Container security platforms check images for outdated components and enforce hardening measures before deployment. Model registry checks ensure that only validated, signed, and provenance-tracked models are allowed into production environments. Governance dashboards consolidate findings from these tools into a single view, making it easier for executives and security teams to oversee compliance and risk. These tools reduce reliance on manual effort and minimize human error, which is particularly important in large organizations with numerous models and rapid release cycles. By operationalizing best practices, tooling turns secure SDLC from aspiration into reality. Common pitfalls can undermine even well-designed secure SDLC programs if not addressed. Neglecting security during the planning phase often results in reactive fixes that are expensive and incomplete. Relying on late-phase remediation creates inefficiencies and allows vulnerabilities to persist far too long. Ignoring AI-specific risks, such as adversarial evasion or data leakage, leaves pipelines exposed to threats that traditional practices may not cover. Weak monitoring after release creates blind spots, giving adversaries opportunities to exploit systems while organizations remain unaware. These pitfalls reveal that secure SDLC is not just about processes but about discipline. Avoiding them requires commitment to early planning, continuous updates, and adaptation to AI-specific challenges. Otherwise, the lifecycle risks becoming security theater rather than genuine protection. Scaling secure SDLC across enterprises requires balancing consistency and flexibility. Standardized templates for datasets, training jobs, and deployment pipelines reduce variability, ensuring that baseline security measures are always present. Automated workflows enforce checks across distributed teams, embedding security into day-to-day processes without creating bottlenecks. Centralized policies establish clear governance, while distributed enforcement ensures accountability at the team level. This structure enables large organizations to secure dozens or even hundreds of models simultaneously without overwhelming security teams. Scaling ensures that practices proven effective in small projects can be extended enterprise-wide, providing consistency of protection while accommodating diverse business needs. For AI-driven enterprises, scalability of security practices is as important as scalability of compute. The benefits of a secure SDLC are substantial, extending beyond technical improvements. Reduced exposure to attacks means fewer incidents and lower likelihood of costly breaches. Predictable risk management enables smoother planning and more efficient allocation of resources, avoiding last-minute crises. Smoother audits come from having compliance built into the lifecycle, with documentation and evidence ready for review. Increased trust is perhaps the most important benefit. Stakeholders, whether customers, regulators, or internal leadership, gain confidence that AI systems are not only powerful but responsibly managed. In an environment where public confidence in AI is fragile, this trust becomes a competitive advantage. Secure SDLC demonstrates that innovation and responsibility can coexist. Limitations and trade-offs must also be recognized to set realistic expectations. Implementing secure SDLC often introduces resource overhead as teams need to adopt new tools, processes, and staff expertise. Development cycles may slow due to additional checkpoints, causing friction with teams accustomed to rapid iteration. Cultural resistance can arise when developers see security as a barrier rather than an enabler. Specialized staff, such as AI-focused security engineers, may be scarce, making adoption challenging for smaller organizations. These trade-offs remind us that security is not free, but the cost of insecure systems is far greater. Organizations that address these challenges with training, communication, and phased adoption can make secure SDLC both effective and sustainable. The strategic importance of a secure SDLC lies in embedding security into the innovation process itself. By treating security as part of design, development, and deployment, organizations prevent vulnerabilities from accumulating until they become crises. This integration ensures that AI advancements are built responsibly, balancing speed with safety. Regulatory obligations are easier to meet, since compliance evidence is generated naturally through the lifecycle rather than bolted on at the end. Protecting enterprise assets, from sensitive datasets to proprietary models, becomes systematic, not ad hoc. Most importantly, public confidence in AI grows, as stakeholders see security not as a patchwork of late fixes, but as an integral principle of development. Strategic importance comes from demonstrating that security and innovation are not opposites, but partners in delivering trustworthy AI. Embedding security into AI innovation also protects against systemic risks. Enterprise-scale AI relies on massive compute clusters, large datasets, and complex integrations, all of which are attractive targets for attackers. A secure SDLC enforces discipline across these moving parts, ensuring that even as systems scale, they do so with guardrails intact. This consistency reduces the likelihood that growth introduces unmanageable vulnerabilities. It also reassures regulators and customers that scaling is deliberate and responsible. By anchoring innovation in secure processes, organizations avoid the false trade-off between progress and protection. Instead, they demonstrate that responsible practices can accelerate adoption by reducing fear and uncertainty. Meeting regulatory obligations is another dimension of strategic importance. Data protection laws, sector mandates, and ethical standards increasingly govern how AI must be designed and deployed. A secure SDLC operationalizes these requirements, ensuring compliance is a daily activity rather than a last-minute scramble. Evidence of compliance, generated through audit trails and lifecycle checkpoints, strengthens organizational credibility during reviews. Regulators expect proactive governance, and a secure SDLC demonstrates it. For organizations, this not only avoids penalties, but also creates opportunities to operate in sensitive or regulated markets, where trust and compliance are prerequisites for participation. Protecting enterprise assets is at the heart of a secure SDLC's value. Datasets, embeddings, model weights, and pipelines represent not just technical artifacts but business-critical investments. If stolen, tampered with, or leaked, they can erode competitive advantage and expose organizations to legal liabilities. By embedding safeguards into every lifecycle stage, data preparation, training, deployment, and operations, a secure SDLC ensures these assets remain protected. Encryption, provenance tracking, and version control are not optional extras but standard practices. This approach reframes security from being about defense alone to being about stewardship, preserving the value and trustworthiness of assets across their life cycle. Sustaining public confidence is the ultimate measure of a secure SDLC's impact. In a world where AI is under scrutiny for bias, misuse, and opacity, organizations that can demonstrate lifecycle security gain trust. Transparency from audit trails, accountability from governance, and resilience from monitoring show that risks are actively managed. Customers, regulators, and employees alike gain confidence that systems are not only functional but responsibly built. Public confidence fuels adoption, as people are more willing to use AI they believe is safe and accountable. By embedding security throughout the lifecycle, organizations strengthen not just their defenses but their reputation, turning security into a competitive differentiator. In conclusion, the secure SDLC for AI is a structured approach that integrates security across planning, data preparation, development, training, validation, deployment, and operations. It aligns with governance, equips developers through training, and enforces discipline through continuous integration. Metrics, tools, and scaling strategies make the process measurable and sustainable. While it carries trade-offs in cost, time, and culture, the benefits: reduced exposure, smoother audits, predictable risk management, and stronger trust far outweigh them. Secure SDLC is not just a defensive strategy, but a strategic enabler, ensuring AI systems are both innovative and resilient. As we move to the next episode on AI incident response, the progression is clear. Secure SDLC reduces risks, but when incidents occur, structured response ensures resilience. Together, they create a complete defense cycle for enterprise AI. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.